When you put an action inside a self-executing AI loop, small inputs multiply with massive compounding speed. This graph illustrates the core financial difference between standard applications and autonomous systems. Standard chatbots incur linear costs. You pay per prompt. But give an AI agent the ability to chain its own prompts together, and those costs climb exponentially. This shift requires developers to adopt a new role, the token CFO. You are no longer just managing logic. You are managing a strict budget of compute. The primary financial danger of an agent isn't that it fails, but that it gets trapped attempting to succeed. An unoptimized agent stuck in a reasoning loop can autonomously drain a monthly API budget in a single afternoon by making hundreds of calls before you even finish your coffee. To prevent this, we must master the math of autonomy and deconstruct the hidden architectural taxes that drain API credits. Building viable AI agents is a management challenge. The code dictates the logic, but the architecture manages the microeconomy. Most autonomous agents utilize the React framework, shorthand for reason and act. For every task assigned, the agent follows a cycle. It generates a thought, executes an action, and registers an observation. The cost vulnerability here is that every new thought requires a full API call. That call must ingest the entire history of every previous turn to maintain context. Imagine an agent assigned to fix a bug in your code. It takes 5 turns to identify the error and apply the fix. Turn 1 reads 1,000 input tokens, generating 200 output tokens. Cost half a cent. Output appends to history. Turn 2 reads 1,200 tokens. This compounds 1,400, 1,600, up to 1,800 by turn 5. Total task processed 7,000 tokens for 3.5 cents. A standard chatbot achieving this same result in one prompt would cost half a cent. The agentic loop creates a 7 times increase in price for the same result. Costs in an agentic system do not scale by the number of steps taken, but by the compounding weight of their own history. The agentic nature of these systems comes from tools, external functions like web searches or database reads. To use them, the AI needs to know they exist. These tools are passed to the model as JSON schemas embedded directly in the system prompt. Equipping 10 tools creates a 3,000 token tool tax embedded in every prompt. In a 10-turn loop, you pay for those 3,000 tokens 10 separate times. That's 30,000 tokens spent simply to remind the AI it possesses a search button. To eliminate this bloat, developers use a proxy layer, or the Model Context Protocol. Instead of sending all definitions every turn, we implement a dynamic injection strategy. The model only receives the full tool definition when it specifically requests a tool discovery step. More context is not better. Precision in tool injection is what keeps costs from spiraling. Controlling this flow is called state persistence. It is the primary mechanism for stopping budget bleed. Without state management, an agent missing a parameter can enter an infinite loop, spending hundreds of dollars on a single task while you're away. The immediate fix is a hard cap in your code. Implementing a max iterations equals 10 parameter acts as a necessary kill switch. For deeper tasks, we use rolling summarization. At turn 6, a lightweight model compresses the first 5 turns into a single 200-token summary. For subsequent turns, the agent only receives this compressed summary plus the new data, flattening the cost curve. The next technical optimization is KV caching, which moves state management from the developer's code to the API provider's hardware. By caching static system instructions and tools at the API level, providers avoid reprocessing them every turn. This yields a 90% discount on those redundant tokens. Treating the context window as a strictly managed compressible state is the key to a sustainable architecture. The objective of these optimizations is to reach the economic break-even point, where an agent becomes cheaper than human labor. We calculate this using the ROI formula: human hours saved multiplied by the hourly rate minus the API costs, all divided by the initial cost of developing the agent. Consider a case study: automating lead scraping for a travel site. A human virtual assistant costing $5 an hour can process roughly 20 leads in that time. This places the human baseline at exactly 25 cents per lead. An optimized AI agent, using the state management we've discussed, processes the same lead for 4 cents in tokens. The AI is 6 times cheaper per task. While building these architectural layers requires more engineering time upfront, the 21-cent margin per lead adds up quickly. In high-volume operations, the project covers its own development costs within the first 1,000 leads. Once the architecture is sound, the final step is refining the text itself. In Module 5, we cover prompt compression to shrink these costs even further. True autonomy is not defined by intelligence alone, but by how economically scalable the system's architecture can be.